So good morning, everyone. My name is Alex Pascini. I'm the Business Development Manager here at AWC Water Solutions and the Water Treatment Specialist. Today we have John Sainas, which is a Vice President of Business Development and one of our senior water engineers here at AWC. Today we're going to be covering everything that has to do with Moving Bed Bio-Reactors, MBBR. We have covered wastewater before and modular wastewater treatment plants. Today we're going to get a little bit more into the nitty-gritty or the details of how these work. It is a biological process, so it's more than just bugs. So let's get started. So this is now episode number 12 of the list that we've been going through. You'll see that every single week we kind of keep adding more. This is a lot of these topics that people are emailing in about and asking for more information on either technology or on different contaminants. So you'll see we continue adding to the list. Next month, or this month rather, October 1st, it's now we've kind of covered it as Emerging Contaminants Month. So we're going to be adding a few more, which includes microplastics, PFAS, cyanotoxins, and one for dioxin, which will be progressively going through the next couple of weeks. So stay tuned. For those of you that are new to AWC Water Solutions, we've been around for 40 years. We design and manufacture water treatment plants. We have over 500 plants worldwide. This, of course, ranges on the potable side, of course, on the wastewater as well, which is what we're going to be covering too. And then we break it down to skid-mounted systems. So this includes anything that has to do with desalination, ultrafiltration, or pressure filters if you're going after metal. So as promised, today we're going to focus on MBBRs. Let me make sure we add everybody else that's logging in a little late. Good morning, Ken. So with that, John, if you want to share your screen and take it away.
Yep, thank you, Alex. Let's switch on here. Everyone see my screen?
Not yet. Go ahead.
Okay.
There we go. Now we're good.
Good. Super. Yeah, I just would like to make one little correction. I'm not going to be talking about everything there is to know about MBBRs. We've only got 15 minutes or so, so we'll keep it brief and high level, and just move forward here to our first slide. Hang on a sec. So what is an MBBR? So Moving Bed Bio-Reactor or biofilm reactor. I've seen it both ways. Essentially, it's another form of aerobic wastewater treatment, typically using air blowers and air diffusers to raise the dissolved oxygen level. And everyone pretty much knows that game. It originally was developed in Scandinavia by Kalnes for high-strength fish waste, and over the last 40 years, it's gravitated over to North America, and it's become quite popular now for various application reasons. The key differentiator from most wastewater processes, aerobic wastewater processes, is the use of the small carrier biofilm chips. And that those chips are actually semi-buoyant, and they support the biofilm, enabling a much higher concentration of organisms within the actual tank volume. So a lot of benefits towards that. And you'll see them popping up now in many different areas, domestic sewage, of course, but also because of the concentration of the aerobic organisms, microorganisms, they actually are very, very good for high strength waste. And I've listed a few of them there. We see them in ammonia removal, leachate treatment, and some new evolutions going on now with lagoon cold weather nitrification. So the basic components of a MBBR system is the bioreactor, and you can see here in a modular plant that we would manufacture. The first zone is the aerobic, is an aerobic zone typically used to remove the BOD preferentially. Now, with an MBBR, if you need to nitrify, it's important that you remove the BOD first, and then the nitrification organisms can actually take over and do a very efficient job of reducing the ammonia to nitrate. And this is typically done with these two tanks, and you'll see right the top right corner of the first tank, there's a media retention screen which retains the media in the tank, and you can see the aeration grid in blue at the bottom. So essentially coarse or medium bubble aeration is used, and in part that is to basically impart good mixing on the biochips to assure that they're kept sort of agitated and sloughing the biofilm off as required. The second tank there again is on the is preferentially for ammonia removal, and again it has a screen which limits the prevents the chips from moving into the downstream clarification process. In this specific example, we've actually shown a hydraulic flocculation zone where, if necessary, we can add a coagulant or a polymer just to help in the settling or the clarification and settling process. And hydraulic, of course, keeps it very, very simple as opposed to having electric mixers or things of that nature. The bottom right-hand corner, you can see a very brief little picture of what the media chips look like. So they're basically little wagon wheels, and they're semi-buoyant. There's numerous different manufacturers of these biofilm chips. For a complete system, as with all wastewater treatment plants, we would first start at the right-hand side of the screen with in-feed screens. We like to use something like a 3 or 4 millimeter screen. We don't have to be quite as fine a screen as we'd use in an MBR, which might get down to 2 or 1 millimeter. And the first tank in a typical domestic application would be your equalization tank. So the raw sewage would go through those top screens there and then into the EQ tank, where we would have our pump sets that would basically control or maintain a constant flow, relatively constant flow through the plants. Now again, here's your zone. This is a twin train system with the first zone for BOD removal, second zone for ammonia nitrification, and then the final clarification zone. And in this case, we've also shown a sludge digester. So we would actually take, from the bottom of the clarifiers, we would have a waste sludge pump, and it would pump to the digester where we would maintain aerobic conditions. And that can be essentially just for a holding tank for pump out. It could also be for a 30-day or 40-day digestion to make some certain organic removal requirements. And we can also decant on that to pull off the to thicken it a bit. Now, the back end can actually be two different, either a conventional gravity clarifier or a dissolved air flotation clarifier. So it depends. As the plants get bigger, we find that the dissolved air flotation gets a lot more efficient and affordable and more compact. So this is a picture of a few of the medias that are out there by various suppliers. Very standard medias are in the middle here, and it actually shows the biofilm growth within the media. And some of the specific parameters that are used for specifying the media are the specific gravity. So we want to keep them semi-buoyant so that they help maintain the biomass floating and everything doesn't settle to the bottom. The other one is the internal protected area. And you can see when you look at the biofilm chips that there's certain areas that agitation will not actually knock the slough or knock the biofilm out. And so that is known as the protected area. And that's important to develop the high concentrations of the biomass. Now, just that, that concentration is important because the more biomass that you can put in a tank and keep aerated, the higher organic loadings that you can treat within a given volume. And that's why the MBBRs are very, very popular, because they're very compact bioreactors. And the other, there's a newer development out, and this is by a company called Mutag out of Germany. They are using little foam chips. They are, so it's unique, and we're starting to see more and more of those come in. Now, there are, for nutrient removal, I have been talking about the basic MBBR, which is a straight through process. Basically, the sewage goes through once, there is no return activated sludge, and the solids essentially settle out in the clarifier, and out it goes, pumped out to the tank, and the effluent, clarified effluent, goes to disposal or reuse as the application may require. Now, to get ammonia or nitrogen removal, you need a recycle loop, which would take that nitrate after the second aerobic zone and put it back into an anoxic zone up at the front end of the plant. And this would give you the opportunity to bring down your total nitrogen levels through the denitrification process in the anoxic zone. So there's two ways that the MBBR basically does this. The first one is in the top left corner, where there's essentially a recycle pump put in on the final chamber, and it moves the fluid back through the nitrified water back through to an anoxic zone, where the conditions, the DO levels, are dropped to half a milligram per liter or less, and there you will get your denitrification occurring. And then the other method is known as IFAS, so it's an integrated fixed film activated sludge. So it actually utilizes the clarifier and has a true return activated sludge flow back to the front end of the plant, where it goes into an anoxic zone. So these are just various methods to increase the nutrient removal capability of the system. And certainly, when you get into application design, we can decide which of the processes is better suited for removing the nitrogen. Phosphorus, of course, that would typically be used with a chemical precipitant such as alum to knock out the phosphorus and remove it with the sludge. So I mentioned there's a number of benefits of the MBBR. Essentially, it's a self-regulating biomass. So what happens as the organics come in and the biomass basically oxidizes and grows cell mass, there's a need to control in most plants that waste sludge operation. And the MBBR, it doesn't require that. As the biofilm grows and it gets out of its protected zone, it basically sloughs off and is basically brought into the clarifier and removed. So there's very, very little you need to do to operate these plants successfully. And that process also helps as loadings change. What will happen is if we get a large organic loading coming in, the biofilm will just grow. There'll be more biofilm on the chips. As the loading drops off, the biofilm will slough off. So it self-regulates itself and minimizing the operational support. It's also, importantly, at steady state. You just basically keep the fluid going and the aeration on, and it's doing its job. There's no other control requirements. It's tolerant to toxic upsets, and this happens if we get a transient low toxicity going through the system. Essentially, as that fluid moves through the plant, the organisms are somewhat protected within the biofilm, and they'll bounce back and become much more active quickly than a conventional plant. So these plants will bounce back a lot faster than from a toxic situation. Again, I described the rapid loading changes, how it accommodates that. Very simple equipment, low maintenance. And one of the big things we find for older communities, especially on the coast where there's lots of rainfall and things like that, and we can have peak hydraulic flows of 10-to-1 or 12-to-1, meaning that they can get wet weather flows 10 times or 12 times the average dry weather flow. A lot of plants can't handle that. They'll wash out the biomass and you have a long time to recover. Whereas, interesting enough, the MBBR actually, the biomass is actually retained on the chips and it will not wash out. So as soon as that peak flows over, it's back and working. So it's a very, very good application for that situation. And a couple other things, the compact footprint gives it a lot of versatility. It fits into tight spaces on industrial sites. So if you got to squeeze it into a corner somewhere, it's very effective because it's compact. Like an MBR is compact, we can actually take existing tankage and double the capacity or triple the capacity going through that plant. And that's a very cost-effective approach if there are capacity limitations. And not only, of course, hydraulic, it's also the loading, the organic loading. So if a new industrial process comes into a plant, we can actually increase the organic removals required. And because it is compact, we can also provide these plants as modular solutions. So basically, complete plants can be shipped, relatively large plants can be shipped direct to site and for plug and play installation. So this is just a large plant that we finished about 2 years ago, and it shows three MBBR trains with the zone 1 and zone 2, followed by, and these were done in concrete. There's a 3D picture coming up. And it's followed by 2 modular DAF trains. And we really like the DAF trains, Dissolved Air Flotation for clarifiers, just because they're the MBBR sludge tends to be quite light and wants to float. So by far the most efficient way to remove it is with the dissolved air flotation. And that also gives you a huge advantage in sludge management, because instead of getting like a 0.3% sludge out of a conventional clarifier, we're actually able to get 3% or more out of the dissolved air flotation, greatly simplifying sludge management. There's a picture of the concrete tanks with the modular dissolved air flotation clarifiers tucked away in the corner there. And one of the big factors with the tanks is cost. Obviously, the more economical you can build a reliable tank, more economical you can make your plant. And certainly a lot of MBBRs end up going into glass-lined, steel-bolted tanks, and they just provide a great dollar value in the sense of capacity for a given capital dollar. So that's a quick overview of the MBBR, and certainly Alex and I are around for a few questions if you have them.
Thank you, John. That was excellent. I'm going to go ahead and open the floor for any questions that you have. You can either punch them in on the top right. You're going to see they've changed the interface a bit, but on the top right, you'll see that there's a chat box, or if you want to turn on your mic, don't be shy, turn on your camera. We encourage it. While some of you work up the courage to come up with some questions, I have one for you here, John, that came in earlier. So you had mentioned using different clarifiers after an MBBR process. Is there a specific clarifier that you would recommend?
Yeah. Well, I actually covered that briefly here, but because of the nature of the MBBR sludge, and also due to the compactness of the actual clarifier systems and the ability to provide modular, high volume modular solutions, we really believe the dissolved air flotation clarifier is the best approach. And also the dissolved air flotation, with properly set up, it'll provide under 10 NTU effluent quality, which basically allows you to achieve very good effluent quality without post-filtration. So yeah, our recommendation is dissolved air flotation. With smaller plants, sometimes the gravity clarifiers are a more affordable, effective solution, just because they're a little bit simpler than the dissolved air flotation.
So a follow-up question to that is, if we had, say, an industrial process where we're using MBBR for some wastewater, industrial wastewater, would you still use DAF, or would you potentially use another clarifier?
Yeah, the industrial processes tend to be much higher strength, and typically DAF becomes actually, and I'm thinking this through, it's an interesting question, but typically as you get higher strength, you actually get quite high levels of waste coming out of the MBBR. And at a certain point, you would tend to find your conventional clarifier might run into problems. Now, in summary, I would have to say that, again, for larger applications, the dissolved air flotation would be the correct approach. For smaller applications, again, I think the conventional gravity clarifier will also do a good job.
Okay, thank you. I have Terry. You had a question? Go ahead. You raised your hand there.
Yeah, I'm just looking at this process, and I'm thinking of some of the applications industrially. What would concrete tip-up construction applications that what you see around all over the world or the country now, where they build these buildings overnight, and the concrete is already prefabricated someplace, and they just tip it up in place. Could that be an application, being that you're using molded steel tanks for the MBBR? Maybe the rest of it could be also prefab, or have you done that at all up in Canada, or have they ever done that to simplify things like this? Thanks, John, for your expertise.
Well, Terry, so that question is about the actual building for that we would house the tankage in.
Yeah.
Yeah, I'm a great fan of pre-engineered or concrete tip-up structures. You know, they're basically, you know, my belief is the big box stores use these things universally for a given reason. They're amazingly affordable for space, and I think for communities or industries that are looking for affordable treatment, I think it's a very affordable way to go, and we could either slide in, you know, modular tankage in the sense of our square tanks, or we could also slide in or erect bolted steel tanks inside.
Okay. I have another 2 questions actually here from Mr. Liu. Sorry, I don't want to butcher that name. Go ahead if you want to turn your mic on, or do you want me to read through these?
Sure, Alex. Hi, John. I've got 2 questions. The first one is you have mentioned the depth thickener is a preferred way for the sludge thickening. So my question is, what type of the nozzles you are using for the depth thickener?
Are you talking about the aeration nozzles at the bottom?
Oh yes.
Yeah, we have a proprietary nozzle. It's you know, essentially an orifice with an impingement plate to create the microbubbles. Mm-hmm. And yeah, we use that and vary the actual, you know, dimensions of the orifice diameter and the impingement distance to meet for each application. So it's yeah, that's what we typically use.
Okay. So after the meeting, do you mind to send me a cut sheet, and I want to see that how you are going to deal with the clogging issues of the nozzles related to the sludge thickening?
Yeah, well, the nozzle, the clogging of the nozzles is really about the quality of the water that's used in the recycle process. Mm-hmm. You know, so if the clarifier is working well and you have the required pre-filtration in front of the saturator or the saturation pump, then you won't have that nozzle clogging or you'll reduce the nozzle clogging issues. So that's important.
Okay, and so what kind of pre-filter you are using?
Typically, we'll, you know, for our drinking water applications, and this is specifically about DAF, we'll use a standard strainers. But as we get into more industrial waste, we'll tend to use a self-cleaning strainer.
Okay, all right.
So just to wrap this up, we are going to leave a little bit of, we're going to have like a questions and answers session at the very end if anybody wants to stay logged in and go for it. We're sitting at the 26-minute mark here, and we want to be conscious of everybody's time. So I want to thank everybody for joining. Again, if anybody has any more questions, please stick around. We can go through them right now, but we can wrap this up. Stay tuned for next week. We're going to be inviting Dr. Lallis. He's going to be coming in and giving a presentation on microplastics. Again, 20 minutes, that's all we ask. Please follow us on LinkedIn. I am sending everybody a link so that you can actually go in there and have a look at who we are, what we're doing, some of the activities that we're doing. We also, if anybody has missed any of the previous sessions that we've done before, we're all recording them on the channel. I encourage you to log in and have a look. I just sent everybody the link. Please let me know if you don't see it. We can always send out an email. I don't know if you can see my screen right now or not, but for October, because it is Water Week in October and WEFTech is now having their virtual conference, we've decided to take a look at some emerging contaminants. So this month we're going to focus on emerging contaminants only. We're going to be touching microplastics next week. Then we have PFAS. We're going to be covering any of the contaminants on PFOAs and PFOS and PFOAs. We will also following it up with cyanotoxins. We know that as water with with climate change and warming, and cyanotoxins have also been coming up a lot with the perfect combination of temperature with soft phosphates and sulfates in our water. And then we're going to wrap it up at the very end here, week 4, with 1,4-dioxane, which is another one of the emerging contaminants that we're treating. So with that, thank you very much, everybody, and a little shameful plug there with our YouTube channel. All of them are going to be posted on there, so you can take a look. And if you want to rewind on some that you've missed, or maybe take some notes on some of the ones that we've done, please go ahead and log in there. I shared the link with everybody. Can everybody see the link? I'm not sure here. It says it didn't go through. But so with that, I'm going to say thank you very much. Goodbye. If anybody wants to stick around, this is the time to do it. So thanks again, and I will see you next week. Goodbye.